Yeah, this. Oh, we didn't do this. I thought we did this in class. Did we not?
I think we did one.
Oh no, we didn't do these. Right, so we have 2 homeworks to do then. Yeah.
Two
Yeah.
types.
Two.
Types of homework.
2 kinds of homework. Correct. Okay. Let's have a look at the first one here. So first one is the couples. A girl opens a 4 centimeter lid off of a bottle by applying a 1 Newton meter force.
Yeah.
What was the force? Oh, sorry, turning force of 1 Newton meter. So there's a force here, there's a force here, and a distance of 0.04. So the total turning force is Fd. This we're told is 1. This is what we want, and this we know. So the F is that.
25.
Okay. 2. Can I scroll down?
Yeah.
Do you have that? Number 2. A braced cantilever is supported by a stay. The stay is 10 meters above the hinge, and the beam is length 24. So this is 24 centimeters. And the stay is 20. Now this is 10. Now somebody tell me why I draw the stay here. Maybe it was like this. How do I know that it must be like this?
Because it's longer. It's 26.
Pythagoras.
Yeah.
Has to be 26 from Pythagoras anyways. Because I told you the 10 and the 24.
Because it's longer than 24.
Oh yeah, so like it couldn't be.
The height.
Yeah. So, what is the tension? Right, first thing I want to do is get this angle here, theta. So, can you hit this in on your calculator? I'll open up mine.
22.6.
Oh, good thing I have one good student. 22.6 degrees. Okay. So, if you look at the tension here, you can resolve that this way and this way. That's T cos 22.6, and this one's T sine 22.6. Yeah. We'll take this as the turning point, and here's the weight here. The weight is 25g.
Could we make that into a triangle?
Make what into a triangle?
The T cos T sine.
Oh, if you prefer, you mean to put
No,
it here?
like to find T.
No.
Can we make it into a triangle and then
No.
do Pythagoras?
No. You don't know enough to do that.
Hmm?
You don't know enough of the sides to do that. In fact, you don't know any of the sides.
Oh, because T.
Yeah. Now, this turning force here will equal the turning force here. This distance is 0.12 times 25g, and that should equal 0.24 times T sine 22.6. So, you did it this way, Fawn? And what answer did you get?
319.09.
319.09.
9.09.
That's the T. So this is saying the clockwise turning force equals the anti-clockwise turning force. Yeah.
0.12 is...
The distance from the turning point to the turning force.
Which is
Yeah. Cool. You're making that look.
How can I find the video?
The what?
The video you YouTube?
I don't know about it.
It have a lot.
I don't. Oh, you just mean how can you search? Is it? Yeah, watch. YouTube.com. And then here. And then, no. So click the search button here. Watch. And let's say we type in,
It's not projecting.
uh-huh. Click this, there's a search here.
It's not projecting.
Of course not, because it's not on. That projector is for this one. That one is for this one. So you'll have two images on the screen at once.
Let's see which one is more powerful.
I have a feeling it'll be that one.
Oh no, it's not.
It's not?
I don't think so.
I know, it's warming up. It's warming up. What the heck? Oh yeah, my calculator, I forgot. Hang on, let me just, there.
Oh, two videos away, 2000.
Sorry about this, Fuang. But on the YouTube channel, there you go.
Oh, yeah.
You can see there's a search here. So you could type in physics, moments, principle of moments. And then, there it is there, see? 1 day ago.
But it's like the same as the September student.
No, this is the one we did because it's 1 day ago. And then this is what the September students did 3 months ago. What?
I'm confused.
It's not
But
confusing.
it's the same name.
And it's the same lesson.
It's okay.
Yeah. What?
You could watch both.
Yeah.
They're the same thing, technically.
Or you can just look at when it was posted.
Yeah.
Okay,
The date.
3 months
1 day ago, 3 views. 3 months ago, 24 views. Oh,
Always
yes.
one of the two.
You remember this? Oh, okay. Right, any more questions?
Okay.
Off we go.
But I can't find the tree form.
That's because I didn't upload
If you
it
turn it
yet.
back on.
Yeah.
Huh?
If you turn it back on.
Please, no, press button again. Oh, goodness sake, off. Press power button again. Off.
Fuck. Puncher.
Off. I just might as well just hold it.
Yeah.
Yeah. It has that sound of shutting down, but it's gone completely. Okay.
We're 2 videos away from 2000.
Am I?
Yeah.
Where did it say that on the page?
I think it's also written. 1980.
Ooh, I must do something today to celebrate then. Right. Number 3 now.
Treat us all.
Yeah, sure. Right, number 3. A braced cantilever supports a 40 centimeter rod of mass 10 kg. So this is a 40 centimeter rod. The strut is 50 centimeters long. So it's like this. So that 40, it's going to be like a 3, 4, 5 triangle. 40 centimeters, 50 centimeters, and this side, 30 centimeters. And the force, look guys, look. This one here is 10G. And there's a upwards force here, a reaction force. Yes?
Reaction resulting.
It's being supported by this.
So is that like to a rope or is it like a stick?
Rod.
Rod.
Oh, this? Yeah, like a rod. Question?
Why it's not the down?
Pointing down?
No, the down.
Huh? Diagonal?
No,
Like this?
the
Like this?
50 and the 50.
Oh, hang on, maybe I misread. The strut is 50, 40. No, that's right. 30, 40, 50 like this.
Yeah.
Yeah. So what's your question?
You said the reaction force is between the 40 and the 50, right?
Yeah.
But why it's not between the 30 and the 50?
Oh, there is. I haven't drawn it yet. Give me a minute, please. Yeah, there's a reaction here and there's a reaction here.
The up and the down.
Oh, here? There is, but we don't care about this because we're only looking at the rod. So we don't care what happens here or what happens here.
The reaction force is down, right?
Which one here?
At the wall.
At the wall?
I think it's down. Upwards.
Let me hang on. Brace cantilever force. Yeah, actually, let me just double check that for you.
Diagonal to the right.
I'm just wondering now, is it diagonal or is it vertical? I think it's diagonal. Yeah. Because if you think about it, there's a reaction at the hinge. So, what does this rod want to do? It wants to fall down, slide down. So there must be a vertical reaction. But I suppose what's a little bit different here, or maybe it's not different, is the rod trying to be pulled out or pushed in?
Pushed in.
Yeah, what's the wall doing, I should say?
Pushing it on.
Is it? See, because I'm picturing this wants to fall away from the wall like this.
Well, from what you said, you would like the wall is always pushing out. That's why.
See, I think but that's when you had like a rope. This is different. I think we should draw the reaction instead of going out, going in, and then this one is going. See, this one I think is running in the same direction as the strut, because it's like the tension, except it's just the other way around. Because if you think about it, just think for it like this. If you had something hanging from here, the tension force is running this way, okay? But the only difference I feel if I replace that with something like this, instead of a tension force running this way, it's holding it up, so the force will be pushing up. You know, the difference is here, this is under the rod,
Okay.
so it's supporting it up, whereas when you have the rope, it's pulling it up. Do you understand? But I feel in both cases the force runs in the same direction as the support. Now that makes sense with a string, of course. If you have a string, it only makes sense that the tension is running along the direction, you know. And that's also what makes me think that the reaction is to the left, because it has to cancel this support to the right. Again, if you look about it like, not that anything too...
So if I'm pulling the pen, the tension is going upwards or downwards?
Oh no, let's not talk about that, because that's not a string, so we don't want to complicate matters. If I have this, or this here, if I have something underneath this,
There's
pushing up, okay, it wants to fall this way. It wants to slide down, and it wants to fall out, right?
Is it being pushed from the back?
So the wall is pulling it back, or the screw is pulling it back.
And it's
Yeah, like this wants to slide down the wall, so there must be a force this way, and also it wants to fall out of the wall, so the wall is pulling the other way. Compare this to if I had a string here. It's like the string is pushing this into the wall, and the wall is pushing back.
Okay.
Yeah. You see, I said this one was difficult, but I hope it's okay now. And in fact, we don't really care about this one, because we're going to use this as the turning point. And this has to be in the same direction, because I have not given you enough information otherwise, because you can calculate the angles here. Okay, now is this okay or not? So far, okay. Right, let's do some calculations then. So, let's get, if I resolve this into horizontal and vertical, this angle is the same as this angle, agreed? Because they're opposites on a cross. And this angle is tan inverse 30 over 50. Opposite over, no, that is totally wrong. 30 over 40, yeah. Opposite over adjacent, this was the hypotenuse. Okay, what's this angle, please?
36.87.
Thank you. This force here is or sine 36.87. If we use our turning force again at this turning point, we get 0.20 times 10g must equal 0.40 times or sine 36.87. And so or equals. If you can calculate that, please. Thank you. 81. I can trust you, right? We'll get confirmation then. Fuan, what did you get?
4.
Okay. Yes? Number 4 now? Oh, sorry, do you have this?
Yeah.
4. So Yusuf, Faisal and Nader. You said Yusuf was at immigration? He was here earlier, and so is Faisal. And Nader? Huh? No one is speaking to him, no one is seeing him. He could be anywhere?
His brother is here.
So he could be anywhere. Alright, number 4 now? Yes?
He was sick. He had
yeah, I heard that.
Problem.
But I didn't hear how that resolved itself. I thought he was going to the dentist.
Yeah, he said he was, but then it was too expensive.
Okay, that's fair enough, I suppose. But I didn't get an email from him. A braced cantilever beam is supported by a 13 centimeter stay. The stay is 5 centimeters above the hinge, and the beam is 15 centimeters long. Now this is an interesting one. The stay is 13 centimeters. Tell me why this is wrong. Why is it wrong to draw it like this? Yeah. This side would need to be longer than this, and it's not, it's shorter. So it actually doesn't quite reach until the end. It will reach to something like here. Now that's 13. Now, if you think from Pythagoras, if this is 5 and this is 13, then how much is it from here to here? It has to be 12, doesn't it? And if the total is 15, how much is this piece? 3 to make the 15, right? So here's the weight in the middle. What is that? 20G. Here's the tension here. So let's resolve the tension again. This angle here, theta, is tan inverse 5 over 12, what's that please?
22.6.
22.6. This one here is t sine 22.6. And again, by using turning forces, we can say 0. Now be careful, it's 0.075, not 0.06 y. Continue. Why is the distance 0.075 and not 0.06?
Because it's not going to bend.
The weight is in the middle.
The middle of what?
The middle of that.
Oh, the middle of that?
No, that.
Oh, not this.
No.
That. Okay. The middle of the 15 centimeters. Remember, it's 15. So the weight is at 7.5 centimeters. Remember that, yes?
Yeah.
And that's equal to, and what's the distance from here to here? 12. And the turning force here is the vertical one, which is t sine 22.6. Now we're not quite finished because I asked for the reaction here, but I need to get the t first. T is 319.1 newtons. Yeah. Okay, we have to continue. Just write that much down so far, please. Got that? One more sec.
What does the 0.075 represent?
That's distance from the hinge to the weight in the center.
Hinge to the weight.
Yeah.
What
Half
is
of 15.
Half of 15.
It's 15 centimeter
Right,
rod.
0.15.
Divided by 2. Yeah. Okay, continue. So, what you have now, if you draw the diagram, you have a reaction here, which has two parts, an or y and an or x. You also have a weight of 20 g, and here you have a t, which we know, a 319.1 cos 22.6, and then this way is 319.1 sine 22.6. So you can say now, or y plus 319.1 sine 22.6, that should equal 20 g. So what's the or y? And then or x should equal 319.1 cos 22.6. What's the or x equal to?
Why would you just say y and y?
That's the question, wanted the or.
What's the r?
Yeah, this or. So we need to find these two to get this one. Can you tell me the or x and the or y, please? For this one? And the other one? Two nine four point six. So how can I get the or? How can I get the or here? Come on, how can I get this or?
Try the past that.
Pythagoras.
Pythagoras.
Say again, sorry? One more time?
Pythagoras.
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 R equals square root 73.6 squared plus 294.6 squared. Let's calculate that. Square root 73.6 squared plus 294.6 squared, and you get 304 newtons. And finally, I want the angle here. How can I get that angle? Come on, wakey, wakey, wakey.
22.
No. No. Tan inverse. Come on, we did this. How do you get this angle? We know these two.
Yeah, we know R.
Yeah, come on, give me what I want. I want this angle.
Oh.
73.6.
Mhm. That's it. 73.6 over 294.6. I have at least one person awake. What? 14? Are you sure? Okay. Is he right?
Yeah,
Obviously.
So why didn't you say it when I asked? You too shy? Yes. No. Okay. Can we look at the next homework then? When you're ready.
Oh, wait.
What?
Why is that?
Why what? 14?
The answer thingy 12.5.
No.
Gimme.
No, no, 14.
Oh, you did the sign, didn't you? Should be the same answer. What did I say?
Maybe we should do tan inverse.
What number is that? 340.
No.
Yeah, great. Okay. Next homework. Next, yes.
The three theorem.
Three-fourths theorem.
It's really